welcome everyone to the webinar of today on the topic exploring microstructure evolution of cost alloys in 3D space using phase field simulations. And this is our 35th webinar, if we have managed to count, for a period of 2.5 years, I think, within metal and polymer component manufacturing. And if you switch to the next one, here you actually can see a list of the ones registered for today. Maybe someone missing, some late registrants missing on the list, but as you see, there are quite a lot of representatives from all over the world that are joining, and the number is increasing as we are speaking. So everyone is welcome as they join. And this webinar is a continuation of the WebLearn project that was a funded project of the KK Foundation that ended in December. But since it has been so successful with these webinars, we have decided to continue them on our own, sort of, to have the opportunity to share knowledge within the field. And me speaking then, I'm the guy to the right, Stefan, introducing you, and later on you will meet my colleague Esan. We are part of the management team of if we even call it project, I don't know, of the WebLearn. And but the most important of today is our expert host, Associate Professor Jakob Olofsson, who will soon continue, and together with our external guest, Dr. Janin Eiken, they will present themselves more closely when they start, and we are looking quite a lot forward to your presentation, Janin. And the agenda of today is just this short introduction, and then the presentations will start. There will be some short stops in between for questions, and then ending with a panel discussion, and then we will wrap up within half an hour. 1.5 hours, of course, it says. And just to remind you, since we are recording the webinar, we would like to have your microphones turned off during the meeting. If you have questions during the presentations, do write them in the chat, and we will keep an eye on that and address those questions towards the end. And once we have the panel discussions, please be active. And unless you want to get your face recorded, have your camera turned off if you don't want to be recorded. And the discussions will be cut off from the recording afterwards, since we will be sharing the recording. And just a reminder for how it works. The next one, Jakob, thank you. Press the mute button down to the left to turn off your microphone and turn off your camera by the side, and then you can open the chat box on the right side to keep it open. And if you write a question, do either write it to everyone or address it to me, Stefan, then, and I'll keep an eye open for it. And by that, I actually hand over to Jakob.
Thank you, Stefan. And again, welcome all of you to this webinar. I'm very happy to have you all here today, and to be able to present to you this topic where I think, Stefan, you said that I was the expert, but today I'm actually not the expert at all. This is the field where Janin Eiken has been working quite a lot. So she is the expert that will be introducing this topic to us today. So I will say some words first here, and then I will leave over to Janin, who will continue and talk about, both give you an introduction to what phase field simulations is, and also show you what you can do with this, with some applications. During this presentation, there will be some call it breakpoints where we will kind of pause, and I will maybe ask Janin some questions, and you will also have the possibility to fill in with the questions during the presentation at some points here. So, or just you can also, as Stefan said, write questions in the chat, and then we will take them in the end here in the panel discussion as we continue. So before I hand over to Janin, I would like to present myself a bit, because not all of you have met me before. My name is Jakob Olofsson, and I grew up here in Småland, this part of Sweden where Jönköping lies, but I would say even deeper into the forests here of Småland. So when I grew up, I thought that I was going to be working in the wood industry, and you see this kind of machines that I was really fascinated about them, how they and be running those types of large machines. However, I learned during school that it was more the technology within them that I was interested in rather than driving them. So I ended up becoming a mechanical engineer and learning a lot about simulations of different types, both on what you typically refer to as finite element simulations, I mean crash simulations, stress strain analysis, lifetime predictions, etc. But also I was very interested in material science and learning more about materials. After my studies, I worked for some years in the engine business or energy sector, rather, working with industrial gas turbines at Siemens in Finspång, outside Linköping here in Sweden, where I was working as a design engineer responsible for the single crystal turbine blades of one of the machines. And so it's quite an interesting field. And then I worked some years in the automotive industry with design of gear shifters and a lot of polymeric parts instead rather than metals. And also I got to work a lot with topology optimization and numerical optimization methods, also with the multi-body dynamic simulations and injection molding simulations and different types of simulations. Then I got in touch with the university and started doing my PhD and been working with what we call the closed chain of simulations, where we look at the simulation chain of castings, going all the way from simulation of the manufacturing of the part, the solidification and heat treatment, microstructure, and going all the way into material characterization and mechanical properties of the material. And my specialty is how to take that into finite element simulations and using what we call local material properties. I've also been working quite a lot with modeling of solidification on a kind of a meso scale, on the casting scale of a cast component. And also with some optical methods like digital image correlation, as you can see an example of here, where you also use kind of numerics in order to understand the materials and so better. So I still work a lot with simulations and modeling in different ways, finite element simulations, mechanical properties, etc. On my free time, I prefer to be with my family and try to do something else. So you can sometimes find me going through Europe in our caravan. And I hope that this summer will be the same, and hopefully passing through Germany sometime during the summer here. With that, I hand over to you, Janin, who is actually the expert for today. I've met Janin several times during the last years at different conferences and the European Cast Iron Group, for example. And I'm very happy to have you here today and presenting to us. So please, the floor is yours.
Yeah, thank you, Jakob. I try to share my slides now.
Yeah, I will stop sharing here. So
So, Jakob, is this working now, or do you see this?
It looks good.
It looks.
Yeah.
So welcome and good morning to all of you. And thank you, Jakob, for inviting me to this webinar and to give me the opportunity to presenting our work here. So today I'm going to talk about phase field simulation of microstructure evolution of cast alloys with a special focus on 3D simulations. So, but first, let me give you the outline. I will start with an introduction, giving some words about me, our group, and the institute. And then I give a short introduction to the phase field method and the MICRESS software, which we develop in our group. And then I come to application examples showing some application to different alloys like magnesium, aluminium, and ductile. So first, who I am. So I already said my name is Janin Eiken. I was grown up in Wilhelmshaven, which is at the north coast. Jakob, can you see my mouse pointer? Or
Yeah, we see it. Yeah. So.
Okay. So I was here growing up in Wilhelmshaven. Then I studied mechanical engineering at the Technical University in Braunschweig. And since 1995, I'm now working at MICRESS in Aachen. And I've been working all the time on phase field modeling and the development of the software, but with different projects, with different application to technical alloys, like starting with steels, photovoltaic silicon, then continuing with light metals, and presently are mainly working on cast irons. This work is also reflected by the title of my PhD, which was a phase field model for technical alloy solidification. So from the personal side, I am married, have 2 daughters, and my hobby is painting. And I thought I could show some of my pictures before coming to equations. So I like playing with color and fantasy, and you may see that a favorite subject of mine are soap bubbles and droplets. So here you may see some inspiration from my work. So sometimes you can say this could be a phase transformation in some way. So is there a link to my work? At the first glance, it seems to be very similar, but I don't think so. I think it's rather a contrast because my work is mainly about mathematics, numerics, and material science, so about equation. But I thought I could show some pretty pictures here before coming to these phase field equations. So now, some words about our institute. It's Accessify is an independent non-profit research institute. It was founded in 1986 as spin-off from the Foundry Institute of the Technical University in Aachen, and we still share the same building with the Foundry Institute. So some parts have moved out. In the meantime, we have now a second location since 2000, the Tech Center, which is also located in Aachen. And so very recently, we have another institute in Cottbus, far away from Aachen. So, and all in all, we are about 70 employees now, researchers and technicians, and the funding is a mixture of research projects in industry. And the scope was in the beginning, when it was founded, it was rather solidification in space, but today it is rather material and casting engineering on Earth and on very different length scales. So we have different groups. So our group is a microstructure simulation group, but there are also simulation on the large scale. Process simulation, mold filling and casting simulations, and there are not only simulation work, but probably major part of the work is process engineering, developing casting technologies, production of ceramic shell mold, and so on. And we also have a lot of work on material research and microstructure characterization, which is also so today I will only talk about our work of the microstructure simulation group, which is mainly phase field modeling, and try to bridge the scale to the different length scale by homogenization and also by integrated computational material engineering. And we developed also software. So I already mentioned we developed the MICRESS software, which is phase field software, and then we have the HOMAT for the homogenization, and we have a platform for ICME. So here I could not find the new picture of our microstructure simulation group here. These are very old pictures. So what you see, we are about 10 people, and Markus Appel is the head of our group. What you see here is a logo of our MICRESS software. So you see we are really proud of our software and always call ourselves the MICRESS group. Okay, and the MICRESS is a phase field software, as I told you, and now I know I should not give too many equations, but I have to at least give an overview about the concept of the phase field method, and we'll start here very simple. So a typical task could be to describe the solidification, dendritic solidification, where we just have one single solid phase going from a liquid, and it could have a very complicated interface, which we do not want to describe explicitly, but we do this implicitly by defining such a so-called phase field. And here the phase field could be related to the local fraction solid, meaning that we have here in the green areas where we have just solid phase, value equals 1. In the blue where it's liquid, the value equals 0. And what is important that we have not a sharp interface, but a continuous change from 1 to 0 with a well-defined profile over a diffuse interface thickness. And in our model, this diffuse interface thickness is just a numerical parameter, which should have no impact on the simulation result. But the advantage of this diffuse interface is that we can now describe the velocity of the interface in form of a partial differential equation and as function of the rate of change of the phase field. So, but to do this in a numerical way, we want to derive it from a free energy functional. So the first step is always that we define our free energy functional, and it looks complicated, but in principle, this is quite simple. We here have the thermodynamic phase energies summed up. So this is the part, the fraction liquid times the energy density of the liquid. We have here the energy of the solid phase. And additionally, we now need the interface energy in between. And in fact, these are all interface densities, so we have to integrate them over the whole volume. Now, when we come to technical problems, we often have not a single solid phase, but we may have multiple phases interacting, and we may also want to distinguish between grains of different orientation. In this context, we now define multiple phase fields. So in our software, we can have theoretically an arbitrary number of phase field parameters. And the concept stays the same. We still have the diffuse interface regions where now several phases may locally coexist with a given profile. And because they are this phase these are handled like phase fraction. We have a unit sum constraint, so they always have to sum locally, have to sum up to 1. And then we define the free energy function in the same way before. So summing up over all the thermodynamic phase energies here, and then summing up over all the interface energies, and then integrating this over the whole domain. Now, what we are interested in finally is to describe the evolution of the system with time. So we need to derive kinetic multi-phase field equation, and this we do based on the assumption that the system will exist into a minimum of the free energy. And this is so we have to form the derivatives of the free energy function. And doing this, we got here now our phase changes. Now we got two kind of driving forces, one from the derivative of the bulk energies, we got the thermodynamic forces, and from the derivative of the interface energy, we got the interface forces, which are here, which we usually distinguished here from these are the junction forces, which gives the junction balance, and these are the mere capillarity forces at the binary interfaces. So now here we have the phase change. Here we have the forces, and they are still related by the mobility of the interface, so to get the kinetics correctly. And now to make it even more complicated, in a typical simulation, we do not only have multiple phases, but we also have multiple concentrations. And then we have to formulate a common free energy functional dependent on both parameter sets. And from this, we derive then a set of phase field equations, and as described before, and additionally, a set of diffusion equations. And these both sets of equations then form the central part of our microsoftware, which we then use to describe the evolution of the phase distribution and the evolution of the solute distribution with time. So I'd just like to mention that the microsoftware is developed since 1996 at MICRESS. But since 2000, but in the first years, we just used this as an in-house tool, and it's only after 2003 that it became commercial. Yeah, I'd still like to mention that, of course, we not only have the phase field and the diffusion solver, but they are accomplished by a nucleation model, a temperature solver, and they are also the stress solver, fluid flow solver, and especially for cast irons, we need also a special volume expansion module. So of course, we need input data for the model, and an outstanding feature of our software is the direct coupling to the thermodynamic interface, to the TQ interface of the thermocalc software, and this means we can directly evaluate Calvert data during the simulation, which gives us a very accurate description of multi-phase, multi-component system. And moreover, it greatly facilitates a simulation because we don't have to look for this data in literature, but just specify our alloy at the beginning, and then this is all automatically read from the database. On the other hand, we also use interfacial properties, and they are more complicated to get. There are some of these interfacial energies in the thermodynamic databases, but then they are based on very simple analytical models, and I'm not yet sure how reliable these are. And another problem is that they are usually just scalar values and then, but in 3D simulation, we did also 3D anisotropy functions because the crystal lattice is usually not isotropic. and such that the surface interfacial energies and the mobilities here are not isotropic. And in the following application, I just like to have a special focus on how these could be defined and what's the problem of getting this data. So now this was already the first time in the introduction. So I should like to give back to Jakob, asking if everything's fine and if there are.
Yeah,
questions.
good. Some questions from my side, just to clarify for my understanding as well.
Yeah.
When we see phase field simulation, you commonly see these cubes that you are showing. But basically, these cubes are all built up by a lot of small elements, right? So you have very small cubes inside this large cube.
So yes.
Just to give an understanding, how many of these small cubes are there actually in a large cube?
So for the understanding, if we have a simulation like this, so the basic phase field method is not digital, it is, but of course, if we it's not discretized, but it's a continuous description. But of course, when we want to solve it numerically, we have to discretize this, and we in our software, we solve the equation by finite differences. And so it really differs. So if I go to 3D, it's just often we have 100 cells in each direction, or 200, sometimes more. So it depends on your patience and your
because I was also
of your computer. In 2D, it's no problem to go to some. Thousands.
Does it require a lot of computational power?
Yes,
usually?
They do, but we spend a lot of time on reducing this power and doing this as performant as possible. But yes, this is it may, if you go to, even if you are 100 times 100 times 100, it ends up with really large numbers, and if you just double it, then so yeah, most time we try to do it as coarse as possible.
Yeah, but I guess it also depends on the morphology of your.
Exactly, you have to so you do have to choose the cell spacing so that it's smaller than the critical length scales and the diffusion lengths. So
you mentioned this effect of anisotropy. Is that what will determine what kind of morphology you will grow, if it will be dendritic or if it will be cubic? Or
this is a major part of what controls it. It's not the only one. It's in combination with all, but I'm going to show in the following examples. So
okay,
come back to this.
Good. Do we have any questions from the audience right now, or and you can raise your hand?
Not in the chat, at least.
No, then I think you can proceed for now, Janin. So
coming to. So I like to start with a very old example on magnesium aluminium alloys, and actually I had some problems to present this, to go back to all this data and wonder how to present it today. But what I wanted to show is that in this project was running between 2006 and 2009, and a typical way of doing a project in this time was you have one partner who is doing the thermodynamic data assessment, which was so in this time there were, in this case I think it was zinc or calcium still missing in the database. So the people from Clausthal, the group of Schmidt-Fetzer, did the thermodynamic data assessment, and we could then use this data base as input for our simulation. On the other hand, we always need a partner who's doing the experiments and the characterization of the microstructure, so we have data for validation. And of course, both the experiments also validate, there are experiments validating the thermodynamic assessment. So this was planned in the very beginning. What was underestimated was the difficulty of getting data for the interfacial properties. So this magnesium, we knew it was a hexagonal anisotropy, so we simply start, we do it just 6-fold, and then it will be fine. And indeed, we were lucky that then some data were published from molecular dynamics calculation for pure magnesium. And this we took as a starting point for our simulations. And then we applied them in our simulation and tried to validate them by experiments. And these I like to show here. So if you have such anisotropy function, if you plot them for the interfacial energy, it appears like a sphere, and with a naked eye, you will not be able to see any anisotropy in this, because this is a very small deviations here from this gives the deviation from the sphere. So, but the problem is that for the actually, it's not the interfacial energy which matters, but it's the interfacial stiffness tensor, which is much higher. And the problem, and it is comes from the derivatives of the second derivatives here of the interfacial energy, or they are added, but the stiffness tensor cannot be plotted in a simple way. It depends on the local direction. So instead, one can, to illustrate this function, one can plot the inverse trace of the stiffness tensor. And this shows here that we have here 6 maxima, which giving here in the hexagonal basal plane. So we also had another paper which giving the interfacial mobility and this anisotropy, which could directly use. So, and we use this in our model. And here we have simulated orientation selection during directional growth of a binary magnesium aluminium alloy. So we started with 50 grains with random orientations. And here, so I should show that we have a special notations. Here we have here, this is a basal orientation, showing here in this direction, and we have 6 prism orientation, which are plotted here on the pole figures. So we let this, so that was my first, and this time it was really ahead of the time to have a simulation with several dendrites going in 3D. And so we could just run it for short lengths, but here you can already see just from the starting 50 dendrites, there are only 9 left here. And from this, the orientations were evaluated, and one could see here directly a clear texture for these prism directions. And one could see that the basal direction, in this direction, they are hardly going, and all the basal directions are here showing with 90 degrees to the perpendicular to the growth direction. So, and it was quite in line with the experiments, and we could also found such data in literature where this was a common selection and growth mode with so the dendrite we're going with one of the prism arms, and you can here see the at 60 degrees angle the neighboring arms, and here you can see this pole figure, this at 60 degrees here you see the shrink of this secondary arms. So this was at the first glance looked quite fine. But when we had a closer comparison with experimental studies from literature, we found that in these studies where additional arms were reported, and one could also see them here in these experiments, but also in all the experiments of our project partners. So these were missing in our anisotropy formulation, and so we now modify the anisotropy function and try to repeat to retain to produce still the molecular dynamics data, but add here this additional arms additional maxima the one desired directions. We did it for both the mobility and the interfacial energy. And using this new function, we were then able to model dendritic growth in magnesium alloys with having all the arms forming, which you could see also in the experiment. So an interesting point here is that we could also see in the experiments, and also in the experiments, this comes from experiment, and also in the simulation, one can also see only 4 of them, while in the from the anisotropy function there should be. So here, this is just half of a dendrite. So here you see 3 prism directions. So if you had the whole thing, there would be 6, but it's going directional. So we just have them. 3 of them, and we also should have 3 of these arms, but 1 of these arms get unstable. So you ask if this anisotropy function is directly imposing the cos mode. It is just giving direction, favored direction, but it does not mean that if there is a maxima that there must be an arm. So depending on the process condition, these arms cannot form because their conditions are not good. So what we know that from under different conditions, these arms may form and they become even dominant. So depending if you run the same simulation with different process conditions. Okay, this was a very old project, and now I want to do a jump to today. So this is a very recent result, and cannot see. So this is a complex aluminium alloy. It's aluminium copper with iron and magnesium and silicon. And this is work which were done by my colleague Bei Zhu, who's also in the audience. And I hope it's I will present her work correctly. Otherwise, she has to complain. So here. So now we did not have to access any data. This was the database for aluminum was quite good, and then all these elements were already included, so one could directly start. And also for the primary phase, it's a simple FCC phase, and for this aluminum phase, the anisotropy is quite well defined. So here, one could directly start with a simulation without doing further assessment. So, and the topic in this project is hot tearing. So, special focus was on the last part of the solidification, starting here from the moment when here the channels, the residual liquid channels start to close. And then until the permeability then stops. And during these moments, from in the last stage of simulation, the permeability was evaluated using our fluid flow solver, and so by here imposing some pressure gradients in different directions. And also the surface area density and the electricity, which I cannot pronounce, so I don't mention it anymore. And the phase fractions were evaluated, so all this morphology data, and the idea was to correlate this morphology evolution to the hot tearing susceptibility. And yeah, and I still like to mention that here at the end of simulation, we also have the eutectic phase. We have here the theta phase going coupled with the FCC aluminium. So, however, these are very small fractions, and these phases were not simulated with, they were simulated with a special model, which we call the unresolved model, which model this the eutectic, which is the two-phase region, like a mixture phase. So we have not resolved the inner interfaces between these two eutectic phases. And we still see that we have here two iron compounds, which are, however, also have only very small fractions and may not play that important role. So the basic idea on this project was to run simulations with different cooling rates and evaluate the solidification path from it, and also evaluate the permeability, and use this data then in the first stage only an existing criteria for hot clearing susceptibility. And yes, and in a further, so this is an ongoing project. And in a further work, I think it is planned that improved criteria might be found, and which takes into account more detailed information, which we can get from correlating directly the simulated morphology to the hot tearing. Okay, so this was already the second example, and maybe I should make a short stop asking if there are any questions.
I can see we have some questions in the from Atsushi in the chat, but I think we will save them to later after we have succeeded a bit.
Okay.
Just a short question from my side regarding this aluminium that you just showed. It's the alloying contents are not very high compared to what we usually see in our cast alloys. I think there was quite a lot of copper. Yeah, 2% copper almost.
So
at the iron. How when we increase the alloying contents, I guess the microstructure and the number of phases possible phases that can form will increase and make it even more complex.
Yes.
Will that make the simulations also more complex and time consuming, or is it not really, or is it anyway possible to solve, do you think, if it's?
I think it will not make it much more complicated, but I cannot say there are always some phases which behave ugly. You can never say before you have not tried.
But
usually it should be no problem if you increase this.
Yeah.
But,
and just as I understand correctly here, when you're simulating the solidification, you also have now, you said you had a fluid flow simulation between the dendrites, basically.
yes.
So it's moving, the liquid is also.
So, but it's not at the same time during the solidification. So we at certain moments during the solidification, we took the structure and then we imposed, or I cannot say we, so Beiju did it, and we imposed pressure gradients and then evaluated the Darcy flow from this in different directions.
Yeah, because I was thinking of that. What is it that drives the flow there? But then it's a pressure gradient. This
was just to evaluate the permeability, and these are just using this representative volume element, which was at a certain time, just to then evaluate the permeability at this time step.
Interesting.
So it's an extra. So we can at this moment just take this and do it as an extra simulation, but with the same software.
Yeah. Okay. We don't seem to have any more questions right now, so I think you can continue now.
So Now, this is about a project which I had on the strontium modification on aluminum silicon alloys. And it is well known that if one add just a small amount of strontium to this alloy, then the microstructure can significantly change and the material properties are significantly improved. And if we go look further on it, it's not only finer. So this what differs is the eutectic structure in between. It's not only finer, but it's also showing a different morphology. And the problem here with these 2D images is that you always see this here as individual particles. But if you have here 3D visualization, and this is here by flip tomography of one of our project partners who provided this one can really see that this structure is connected in the third dimension. And of course, we could not simulate this in 2D, because in 2D, one would have to, at every point, renucleate this phase, which is completely different from a 3D structure where it can go continuously. So here in this, if it's unmodified, you see then we have a rather coarse plate-like lamellar or say flaky structure. If it is strontium modified, it is called fine fibrous, and what is important, it's branching in different direction and multi-dimensional direction. Well, here it's just branching, just in a it is branching, but rather in a two-dimensional way. So how to have this simulate this and why to simulate this? The idea was in some time to understand better the mechanisms between why it is different. What could be the mechanism of strontium to change the growth mode? And actually, we wanted to test two different proposed mechanisms, which are under debate. And there are some groups saying it is the impact of the strontium on the interface kinetics in twinning, which are changing the structure. And the other groups say it's the impact on nucleation, which is changing the structure, because here we have some nucleation sites for the silicon are poisoned, and this changes it. And actually, by our simulation, and the final conclusion was done that both are important and just work if they are properly combined. However, of course, this is very difficult. You can imagine this is different to model in a phase field simulation, because here the different branching behavior, this is really complicated rather on the atomistic scale. So the silicon what we have here are not single crystal, but it's twinning, and it's twinning on a really small scale. And a typical mechanism which one has to know is this, that when we are twinning is preferred because at the edges between the twins, attachment of new atoms are preferred, and so it has a higher kinetics in this direction. So it can go in with a much higher attachment kinetics than the faceted planes. And this is why the twins are preferred. And the idea now is that the strontium atoms may hinder this mechanism, and so they reduce the kinetics in this direction. But on the other hand, they are facilitating complex 3D branching. So, and this experimental observations are that the structures inside the fibers, they are not all the same crystal. Their orientation is continuously changing on a very small, almost atomistic scale. So how to model this? So what we needed here is we could not model all the different here atoms layers for its own, but we wanted to find an effective anisotropy. One taking into account the 2D twinning and one the 3D twinning, and one with reduced kinetic coefficients. So this may look on the first glance rather arbitrary, but there was an idea behind. So the single crystal of the silicon goes with 111 facets. So we have here the set of 111 facets, and now we can have twins, and theoretically we can have twins in all these directions. But if it's unmodified, we only have twin in one direction, and if we just combine all these facets which are here, so these facets are facets of one of the twin, then we end up with something like this. Or when we take all the twin facets in all directions, we end up with this one. So this was the idea behind. However, when we now use these two different functions for the mobility, we found that this did not change the outcome of the simulation. So when we run a simulation where we had here, you could see almost the same, and we had frequent nucleation of silicon, then it was almost not changed. So this has little impact. So we had to take into account the second mechanism, and this is here commonly in an unmodified alloy we have a lot of phosphor in it. So we have just small amounts of phosphor, but it's sufficient to form aluminium phosphides, and these are a potential nucleation site for the silicon, and so we have usually commonly many nucleation sites. However, when we have a certain amount of strontium above a critical value, then strontium aluminium silicides will form before the silicon and can poison these nucleation sites. So then we have here, these are now poisoned, and strontium nucleation of silicon is significantly reduced. So only if we had this in our simulation, so we had now in this simulation taken into account that we had phosphor in it, so it's sufficient phosphor that the aluminium phosphides would form everywhere. And we had here also taken into account the strontium in it. And here it's, and our project partners provided the new database here with the strontium inside. So, and we could, so here, and this, under certain conditions, this strontium silicides become stable before the silicon, and then we get here, these are poisoned, and the silicon will only nucleate in one of the sites, and then we will have really this get this really fibrous modified growth. Yes. However, whenever we had here silicon nucleated on the many aluminium phosphide site, then it was independent of which anisotropy we took. We didn't get modification. However, we would also not get modification if you just use this unmodified anisotropy for its own, and you would just get a finer structure, but not modified growth, fibrous growth. So our conclusion was that we used both, we needed both the changed anisotropy and the effect on the nucleation, and the explanation why we need this nucleation mechanism is that because this nucleation leads to, if we have just a single eutectic cell, it grows with a much higher growth under cooling, and this growth under cooling you can already also see in the temperature evolution here that this is undercooled. And if we have a lot of nucleation, many nucleation sites, then we are always very close to the equilibrium eutectic temperature, and in this case the it will go diffusion controlled, and the interface kinetics have no impact. They do not matter because it's anyway hindered by diffusion, not by interface kinetics. So yeah, I hope it could be understand. I know I usually I have much more slides for this to describe this in more detail, and it's quite complex and it is quite unusual. And normally you say if you have many nucleation sites, then you will get a fine structure. And this is better, but here it's not the case. Here it's really preferred if you have just a few nucleation sites, and then you will get a much finer eutectic structure. On the other hand, it means that you get larger eutectic cells. So here you have very small eutectic cells, and here you have large eutectic cells. So, most people want to have small eutectic cells and fine structure, but this does not really work. And maybe only if you have high pressure die casting, where you have really high kinetic undercooling from the process. Okay, so this was a quite complex application. And then I'm already coming to my last example, but if there are questions now, we can already.
I think you can proceed with this last example also, and then we can take the questions in after that. So.
Okay, so now this is good, work on graphite gauze and ductile cast iron. So this is this work results stem from a project I had some years ago. I'm now working on another project again, but these are quite old data results. So here we first simulated the dendritic gauze of the austenite, which was here we did not. So this is just a part, or should not be the whole austenite dendrite, just a part of it. Actually, we did not pay much attention to this because first we wanted to solve the problem with describing the graphite gauze. Well, I now learned that in future we may have pay more attention also on the austenitic grain structure, dendritic structure, which comes first. So here I want to focus more on the gauze of the graphite, which you see here forms first in the liquid and grows already spheroidal from the liquid. And when it becomes attached in contact with the austenite, you see it's directly encapsulated because these are eutectic phases. They want to go together. And so austenite really wants to go in contact with it, and due to the interstitial diffusion of high interstitial diffusion of carbon in austenite, they can go on and go further even. So you see the graphite can continue to go by solid state diffusion through this austenitic layer. Yeah, and so finally, we end up just here with the austenitic matrix and the graphite nodules inside. So there may be grain boundaries which are not depicted between the austenite, which are not depicted here. And in this project, we just stopped here at so we went from this to this end of solidification, then further down to the onset of the eutectic temperature, but I have not yet gone further. And now I'm currently working on the austenite decomposition to ferrite. But this was not part of this work, and this is still work in progress. So, okay. Now, what should be noted is that we not only have the structure and the face morphology, but during all the simulation, we also simulate the redistribution of the solute elements. And here you see the redistribution of the silicon during the growth. So it is just here, the growth is depicted here. So, and here now we are at the end of the simulation, and you see we only have graphite nodules in austenite, but here it seems that there is still a dendrite from the pattern. This is because they are just frozen, these patterns are just frozen in, and yeah, so you still see the history from the old microstructure. And you can also see that we have silicon is segregating negatively here. So in the end, we get the smallest amount. And what you also see that the highest amount of silicon is in direct vicinity of the. And also here where the primary austenite dendrite had been. Okay, and so this input data for the simulation came from a model castle with well-defined input parameter where we had all the thermal history. And so we put one simulation with different cooling curves. And so on this, from this, we evaluated the silicon distribution maps and compared them then to the experimental results. And you show here already that the distribution in space looks very similar. Yeah, and from simulation to experiment. And but this could also be quantitatively evaluated in a statistic way. So this is what you usually call segregation analysis, where you just take all the values from the field and order them by size. And then plot them, and you can do this exactly the same way for the experimental data. And when you do this, you find a very good agreement between these values. And there are some disagreement at the beginning and the end, but I would suspect this is rather from the bias from the experimental analysis. So, but here we have, I think we might have some bias by the procedure, how to measure it and how to etch and polish it, and all these problems we don't have in our simulations. So, and of course we can do the same for the other alloying elements like manganese. Manganese is segregating positively. So it's so we have the highest values here at the end of the solidification. Okay. And then we compare this statistically, and here also find a very good agreement apart from the first and final points here, which are which I'm not sure if they are really differences or come from the measurements. So here we have some more deviation, but all in all, we can say that here the agreement is quite well, which gives confidence that the databases are fine, and that and also showed that this segregation, the statistic of the segregation was almost frozen in, because we have here different, this is at room temperature and this is at temperature before the eutectoate transformation. So you see that they do not change much after this. So the theory that the compositions may frozen in seems to be realistic. Okay, now I think the thermodynamic databases might be quite relatively reliable by now, seeing these results. What is of course difficult is to model the anisotropy of the graphite growth. And here we have a rather pragmatic approach again. So again, we have a hexagonal structure, but now we have in the basal plane very high bindings, while we have very weak bindings in the other direction. And this means then we can see many different growth forms of the graphite. And the typical growth forms for the spheroidal we have these sectors and new nucleation on top of the sectors, and I try to visualize this in 3D, which was it's just a picture, but so how I could imagine that it could look like. Probably the sectors are larger, but what is clear is that we cannot model it in this way. And instead, I simply choose a multifaceted anisotropy function. And we have here many different facets, which are more or less randomly chosen with a certain distance. And the values for each of these facets were taken from the literature. They are say that they are C facets. And so we took the values from this here for the interfacial energies from literature. However, I don't have any data for the mobilities of these. So I can only guess this value. So, okay. Now, I still want to show you that when I plot this is not the interfacial energy. This is just a Wolf plot of the. So this is the morphology it would have if it were in equilibrium, but of course it's not in equilibrium during the growth, and so it may during growth may look very different and may have very different growth form. And I want to show you that in a simulation, which I say, I don't claim that this is quantitative in any way, or this just shows that you can have with the same anisotropy very different growth forms. So we have here, you see again, a dendrite, and you should see here is the first graphite forming. This one is already encapsulated. So I presented here the dendrite a little transparent so that one can see this, how it is encapsulated. And you see most of them are fine, completely encapsulated, but there are some which then in some cases you find some degeneration, and I'm not sure why this happened here. And if this is physical in any way, but it happens. And in some cases, you now find that under a certain process condition, that the growth mode suddenly changes to coupled growth. And here you see now you have a fibrous coupled growth, where here you see that the silicon has direct contact to the liquid. And once this starts in a simulation, it seems that there is a critical barrier, activation barrier, which once it is overcome, it will continue in a coupled growth. So, and then it goes on about my simulation. For some reason, my simulation is not working. So I hope it's going on. So you can see now it's once it happens, it's filling the whole residual liquid instantaneously with this. So at the end, you will see here a very different morphology. And I don't claim that this is physical in any way, because I don't have reliable quantitative interfacial properties here for the system. So I just can play around with these properties. What I wanted to show is that even if I have taken exactly the same anisotropy function for all of these graphite modules, they may end up with very different morphologies. And they can even form here this coupled growth, which because this coupled growth is also just an arrangement of a lot of C showing with the C facets to the outside. And this is something I would like to further investigate in future when we have this change to the coupled growth under which conditions. Yeah. So my present project is rather going now on with the austenite decomposition to ferrite and pearlite, and it will still take some time until I get new results on this side. So I think now this was already the end.
Thank you so much, Janin. Really interesting. I have 2 million questions. We don't have time for that right now. Instead, I would like to hand over a bit to the audience.